All right, hello everyone, welcome to the video. Here we're going to be talking about an issue that comes up in scuba diving. In case you didn't know, scuba is actually an acronym, although it's not written like that here, that stands for Self-Contained Underwater Breathing Apparatus. And so basically it's diving when you have a tank of air that you're going to breathe in while you're underwater for prolonged periods of time. So what happens is you begin with a tank of gas, a cylinder. So here's like the regulator on it, so forth. And this will be connected to like a breathing mask. Okay, and when you're in the boat and getting ready, your tank is going to have a certain amount of pressure. And so let's just imagine that when you're in the boat, the temperature is going to be 30 degrees Celsius, and the pressure in your tank is going to be 304 atmospheres. And then when you dive down deep into the water, the temperature is going to go to some lower value, and the pressure in your tank is also going to drop because gases are going to be sensitive. The pressure in the gas is going to be sensitive to its temperature. As the temperature goes down, molecules have less kinetic energy. They're going to collide with the walls of the tank less frequently, and that's going to manifest as a lower pressure. And so let's say deep down in the cold water, your pressure is down to 281 atmospheres. Our goal in this problem is to use this change in pressure to figure out what is the temperature that the gas reaches once you're down in the cold water. So to answer this problem, we need to use the ideal gas law, but not in a very direct way where we just plug in the numbers. We need to first process the ideal gas law to put it in a form that allows us to relate pressure and temperature and another pressure and temperature. So let's begin here with ideal gas law. And that says that pressure times volume is equal to number of moles times K and then times T. I'm sorry, this is actually number of molecules if I'm using Boltzmann's constant K here. Okay. So the strategy here is to put all the variables that are changing on one side of the equation and the ones that are not changing on the other side. So which variables are changing here? It's pressure and temperature. So I need to leave pressure on the left side but divide through by temperature to get that also on the left side. And since volume is not changing, the tank is constant volume, then this volume is going to move to the right. Okay, so there we go. One assumption here, guys, is that we're assuming that the diver is not actually breathing the tank. So you can imagine, let's say they're just lowering the tank down on a rope. So he's not breathing any of it. Therefore, the number of molecules in the tank is staying constant during the descent of the tank. Okay, so this is very important because now you can see that these three variables, the number of molecules, Boltzmann's constant, and the volume of the tank are all staying constant. No matter what pressure and temperature do, the product of these three molecules is constant, which means the ratio of pressure to temperature stays constant. So if this was the initial pressure and temperature, then later on, if I had a different value, P2 and T2, the ratio always has to be equal to this constant combination of variables. So this leads me to a law that P1 over T1 is equal to P2 over T2. And this is sometimes referred to as Gay-Lussac's law. All of this derived expression from the ideal gas law is one of many. We have Charles's law and Boyle's law, and this one is called Gay-Lussac's law. So now that we have that, we can try to solve for T2. Oh, sorry, this variable right here should be a T. Let's multiply, basically cross multiply essentially, multiply both sides by T2, and then also multiply both sides by T1 over P1. Maybe let's just do that slow, just so everyone's got it. So first multiply both sides by T2. So you're going to get P1 T2. Okay. Now we're going to multiply both sides by T1. Now we're going to divide both sides by P1. And we have this. So we've solved for T2. We now have to just put in our values. And for the pressure, even though we've been given the numbers in this unit of atmospheres, we actually don't have to convert it to pascals, which would be the standard SI unit, because we have the ratio of pressures here. So this one we can just put straight in as 281 atmospheres, and over here 304 atmospheres. Now the temperature, we do have to put that in absolute units. So we cannot multiply here by the 30 degrees Celsius. So we need to add 273 to the 30 degrees in order to convert it into units of Kelvin. And that'll of course become 303 Kelvin. So at the end of that calculation, we will get a value of 280.1 Kelvin. And then, just to go back to our original unit of Celsius, we can now subtract 273 from this, and we'll be down to 7 degrees Celsius. So there we have it. The diver is essentially going from 30 degrees water, which is fairly warm, down to 7 degrees Celsius. And in doing that, the pressure has gone through a big drop. So there's this derivation from the ideal gas law of Gay-Lussac's law, allowing us to relate pressure and temperature. And do you guys please try to understand this derivation, because we're going to need to do this for one of our concept problems in this unit, is taking ideal gas law and trying to relate variables that are changing and isolate them from the variables that are not changing. So this little derivation is a good one to know. All right, guys, that's it for right now. Thank you so much for watching this video, and I'll see you in the next one.